So last week we finished chapter 2, but I will review some of the last concepts that we covered last week. So the first point is let's consider these two examples, right? Just to try to help us better understand conditional probability. So the first question asks, what's the probability of getting ahead second time, right? So we are flipping a coin and we want to get ahead second time, given that we get ahead in the first time, right? So basically the experiment consists of flipping a coin twice, and we want to calculate probability of getting ahead in the second flip, given that the first flip is ahead, right? We got ahead. So, flipping a coin is an independent event. It doesn't matter what you got in the previous flip. So it's always probability is 1 divided by 2. Right? Even if you flip a coin 100 times and you get ahead for all 100 times, probability of getting ahead in the 101st time is still 1 divided by 2. Now the second question is asking, what's the probability of getting ahead twice, right? So here, basically we want to calculate probability of, let's try to write with a different color, probability of first head intersection second head, right? Because we want to get we want to get ahead twice. That means that both times it must be ahead, right? So it's an intersection. Intersection means and, right? And again, these two events are independent from each other. So this is going to be probability of first head times probability of second head, right? And I told you always use this equation with caution, because this is correct because they are independent. Otherwise, this equation is not correct, right? And that's 1 divided by 4. Right? So you see that both of these, both question 1 and question 2 lead to getting 2 heads, right? In both cases, we are getting 2 heads. But in the first case, probability is 1 divided by 2. In the second case, is 1 divided by 4, right? And that's because in the first case, it was conditioned of getting a head in the first flip, right? So we already knew that the first flip was a head, right? And in fact, this question is quite similar to the example that I gave you guys, about families with 2 children. I think this is a better example. So let's explain it here, right? So probability of getting 2 heads, we just calculated, is 1 divided by 4. Probability of getting 2 tails is also 1 divided by 4, right? Because we want to get a tail first time and a tail second time, right? And finally, probability of getting 1 head and 1 tail, right? So when we say we want to get a head and a tail, it means that we don't really care about the order, right? We don't care if the first one is head or second one is a head, right? So that is going to be probability of first head and second tail plus probability of first tail and second head, right? So either first head, second tail, or vice versa. And that is going to be, this is 1 divided by 4 plus 1 divided by 4, right? That's 1 divided by 2. So if we summarize, probability of 2 tails, probability of 2 tails is 1 divided by 4. Probability of 2 heads is also 1 divided by 4. But probability of a head and a tail that is 1 divided by 2, right? And intuitively, this should make sense to you, right? The result that we got. If you flip 2 coins, it's more likely to get a head and a tail as opposed to 2 heads or 2 tails, right? In fact, this is twice as likely, right? This is 1 divided by 2, probability of getting a head and a tail. Any questions? Okay. All right. And there's a statement at the end. Let's read it out. Almost always, when 2 events are mutually exclusive, they are not independent, right? So there was a question last class, if they are independent, are they mutually exclusive? If they are mutually exclusive, are they independent? So we can say that if 2 events are mutually exclusive, they are actually not independent, right? Because independence means that if one of them happens, it doesn't alter the probability of the second one, right? So basically, independence means that probability of A is equal to probability of A if B happened, right? So B doesn't alter the probability of A, right? So for example, I'm flipping 2 coins, and A is the outcome of the second flip, right? And I tell you that, oh, by the way, the first flip was a head. You say, oh, I don't care. It's still 1 divided by 2, right? These are independent events, right? Can anybody say why I say almost always? I don't say always. Is there a case that 2 events are mutually exclusive and independent? There is a case, actually. That's why I say almost. But it's sort of like a weird case. So there are 2 events that are mutually exclusive and independent from each other. There's one case that this can happen. It's a weird case. I just mentioned what it is. That's only if P of A is 0, right? A is an impossible event, right? So assume that I'm flipping a coin, right? It's only head and tail, right? And say, oh, A is the event that number 5 comes up, right? So A is basically an impossible event, right? And so we call A number 5 comes up when I flip a coin, which can't happen. And event B is, for example, a tail, right? Getting a tail when I flip a coin, right? Now, A and B are mutually exclusive because A is an empty set, right? A is impossible to happen. And at the same time, they are independent, right? Because if I tell you that I flipped a coin and I got a tail, the probability of getting number 5 is still 0, right? So basically, A is getting, let's say, 5 from a coin flip, right? And we know that probability of A is 0 because a coin doesn't have number 5. It's not a dice, right? And B is, so event B is getting, let's say, tail from a coin flip, right? So probability of B, probability of A is 0. Probability of A given B, right? So if I tell you that B happened, let's say I tell you that I flipped a coin and it was tail. Probability of A given B is still 0, right? So here we see that probability of A is equal to probability of A given B, right? And that means that A and B are independent from each other. Remember, one of the requirements for independence was probability of A is equal to probability of A given B, right? So this is like sort of like a pathological case because probability of A is actually 0. Yeah.
Yes, if we said like event A is like getting a head and event B is getting a tail, so both of them, they are mutually exclusive, right?
Yeah.
So how they are dependent on each other?
They are actually dependent on each other because if I tell you that, so here if I define event C, as getting a tail. Sorry, event B was getting a tail, so I define event C as getting a head, right? So here, C and B are mutually exclusive. If I flip a coin, I either get a head or a tail. I can't get both, right? And they are also dependent on each other because probability of C is 1 divided by 2, but probability of C given B, what is this? I'm flipping a coin and I tell you that I got a head, I got a tail. What's the probability that it's a head? It's 0, right? I already tell you I got a head, so this is 0. And these two clearly are not equal to each other. So.
Okay, so what's the difference when we're saying like, I mean like how to express it? I have got a head, so it will not affect the second one. I mean, like,
No, this is a different example. So here I'm flipping one coin. Don't mix the question.
okay.
So here there's only one coin. Previous case, there were 2 coins. Okay, so let's look at another case, right? So with flipping coins, independence is quite, intuitive. We know that they are independent intuitively, right? 99% of the time, that's not the case. We have to prove independence, right? So let's look at this case. So here I denote with, a part having a surface flaw as F, right? And I denote the event that, some part is defective as D, right? So first, let's answer the second one. Mutual exclusiveness is almost always easier to assess, right? So to find out if they are mutually exclusive, we just look at the intersection. Can they happen together, F and D, right? And they can happen together, right here, F and D, right? So the answer here is no. They're not mutually exclusive. For these 10 parts, they can happen together, right? So the second one, we answered it first because this is an easier one to answer. We just look at the intersection. Now, the first one requires, some analysis. We have to prove that they are independent or not. They are not independent, right? So we can do a bunch of different things. For example, like in this slide, we calculated probability of D given F, right? So probability of defective given F. So once we say given F, it means that we are in this column, right? So remember, this is a very important notation. Given F means that, for sure F has happened, right? So that part has a flaw. The F has a surface flaw, right? So we divide by 40, and defective here is 10. So this probability, P of D given F, is 25%, right? And then we also have to calculate probability of D, right? In general, what's the probability of a part being defective? So that's total number of defectives. That's 28. I have a total of 28 defectives divided by 400, right? And we clearly see that these two numbers are not equal, right? So since they are not the same, then D and F are dependent, or D and F are not independent. So the answer to this will also be no. Right? Yep.
So every event is a dependent. It's not like a case that it's a mutually exclusive, but like almost every case it's mutually exclusive. It's a dependent, right?
Say it again.
Every two events they are dependent doesn't mean that they are mutually exclusive. But if two events are mutually exclusive, that means like they're almost dependent, right?
Yeah, that's correct. Okay, so we can look at this, we can try to understand intuitively what's going on, right? So intuitively, probability of having a defective part is 7%, right? But if I tell you that, the product that you have picked has a surface flaw, that probability increases to 25%, right? So that means that these two are not independent from each other, right? So there is another thing that we don't discuss in this course, and that's called causality, right? What causes other thing, right? So probably in this case, having a surface flaw causes, products to be defective, right? So, and by the way, this was one way to look at this, right? I really encourage you to do this at home. At home, do the following. Calculate probability of F given D, right? Or we can probably do this here. It's so quick. So F given D is 28, right? So given D, it means that we are in these 28 parts. So I have to divide by 28. And probability of F given D, so F intersection D, that's 10. Right? And we can also calculate probability of F. Probability of F is how many total parts do I have with the surface flaw? That's this 40, right? So 40 divided by 400. Okay? And again, we see that they are not equal, right? So these two are not equal. Not equal. And because of that, they are dependent. Right? Same conclusion. It doesn't matter. There was a third way. Does anybody remember? Either F given D or D given F, or there was a third way to show dependence or independence.
If P of F entered D is equal to P of F times P of D.
Yeah, you're going to go the same thing? Yeah. So the third one, I suggest you also do that at home, So test this one, P of D intersection F, whether that's equal to P of D times P of F. Right? Is this equal to? Right? All three of them always give you the same answer. It doesn't matter which one you use. Questions? Okay. So the next one, the way I basically wrote down the numbers, it leads to independent events, right? So let's check out this one. So again, mutually exclusive, no. Because they have overlap, right? That's the easy part. So again, so this example, the new one is exactly same as the previous one. The only difference is that I'm changing these numbers, right? You see these 4 numbers here? I'm changing these 4 numbers. Otherwise, the question setup is exactly the same as before. So mutually exclusive, no, because D and F have an overlap. And this is the overlap here, right? If this number was 0, then yes, they were mutually exclusive. But this number is clearly not 0, it's 2. And because of that, this answer is no. Right? Now let's answer the difficult part. Are D and F independent, right? Again, we can do the same thing. Here we calculated P of D given F. It's exactly the same as the previous question, so I don't explain. That's 5%. And, the numbers are set up here. These 4 numbers are set up so that if you calculate P of D, you get the same answer. Both of these are 5%. Right? So because of this, in this case, D and F are independent. Right? So you see that these 2 questions are exactly the same, right? And the only difference is that the numbers are changing, right? So for example, for your project, you can think of 2 different events and investigate whether those 2 events are independent from each other or not, right? So basically the way you do that is you collect some data, you calculate probabilities, and you show that, the probabilities, basically they satisfy this equation, so they are independent. Right? Or they don't satisfy, they become dependent. So often beforehand, before running an experiment, we don't know. We usually have a hypothesis, right? So we talk about it later on. So from our, intuition or from physics, we have a hypothesis, and we basically collect numbers to either prove or disprove the hypothesis. So we also looked at total probability, right? So a lot of questions are set up like this, so we have a probability of failure if, my level of contamination is high, and I have a lower probability of failure if my level of contamination is not high, right? So we did this one also in previous class. This is just a review. We wanted to find the total probability of failure, right? So the question says, oh, don't give me, So basically what this number means is that, so this table means that probability of failure given high contamination is 0.1, and probability of failure given not high contamination, so we call that C prime, that is 0.005, right? The question says, I don't care about these conditional probabilities, give me the total probability of failure, right? And the way we solve this is that we drew the Venn diagram and we said that, we either have high contamination or not a high contamination. And failure has overlap with both of these, right? And we calculated the final number, and that was 0.024. Any questions about this? Okay. And then we introduced the Base Theorem, right? And we said that it's useful when we want to calculate probability of A given B, but from our data we have probability of B given A. And this was the example one of the examples that we solved for the Base Theorem. So again, the same question. I have the probability of failure. I have the probability of failure if I have contamination, and I have the probability of failure if I don't have contamination. Now I want to calculate the other way around. I want to calculate probability of high failure. So in this example, so here I'm denoting it with H. In the previous slide, I denoted this with C. It's the same thing, right? So I wrote it as probability of F given contamination in the previous slide. Right? Now we want the other way around, right? And we solved this using the Base Theorem. And it's once you can set up the question, it's quite easy. Probability of H given F is simply probability of F given H times probability of H divided by probability of F, right? And I mentioned that this total probability is usually hard to calculate, right? So here we are lucky because we did it in the previous example. So this guy is going to be 0.024, and we have all the other numbers, right? So that's 0.1 times probability of H, and probability of H is 0.2. So that's it. Right? So let's do another example that's quite similar to this one, right? So here the problem setup is a bit different. So we have a company that tracks the use of its website, and it has found that the more pages a visitor views, the more likely the visitor is to provide contact information, right? So if the visitor visits more pages, of a website, then when that visitor asks for contact information, it's more likely that that person provides the contact info. Right? So we see basically the numbers here, right? So 40% of visitors visit one page, 30% visit 2 pages, 20% visit 3 pages, and 10% visit 4 pages or more, right? And among these 40%, so if a person visits 40% of the pages, probability of that person providing contact info is 10%. And we see that that probability increases, right, as they visit more pages. For example, if they visit 4 or more pages, probability is 40%, right? So what I basically suggest you to do, first of all, is I uploaded the solution to the suggested problems. I highly encourage you to, don't look at the solutions first, right? So do all your best in solving the problems yourself, because all problems in this course, after you see the solution, you're like, yeah, that's obvious, right? But it's important that you do them before you actually see the solution, right? So the first thing you do after you read a question like this is you should try to basically summarize this table in basically like mathematical notations, right? So here basically this 10%, this means that probability of, so let's denote it with something. I don't know what I denoted this here. Oh, nothing. So we can denote providing information as P, right? So you provide information. Given one page, that is 0.1, right? So, and that is this number, right? So this is very important. Once you can figure out, how to interpret the table as, mathematical notations, the problem becomes easier to manage, right? So if you visit one page, probability of providing contact information is 10%, right? And let's write another one of them also. Probability of, for example, providing contact information given 3 pages. So 3 pages, that's going to be 20%, right? So the question wants the total probability from us, right? So if we look at part A, what's the probability that a visitor to the website provides contact information, right? So the question says, I don't know how many pages the visitor is going to visit, right? Just give me the total probability, right? What's the total probability that somebody provides contact information, right? So basically what we have to do, we remember from the total probability, right? So it's usually a good idea to draw a Venn diagram, to make sure we understand what's going on. So a person either visits 1 page, or visits 2 pages, or visits 3 pages, or visits 4 pages or more. 4 or more, right? And this will be providing contact information, right? So we note this guy as P. Right? So probability of P is going to be this part plus this part plus this part plus this part, right? The summation of those 4, right? And that means that, so let's write one of them, right? So for example, for the first part is going to be P of provide intersection 1 page, right? So what's the probability that, provides information and also visits 1 page? Can I say it's the product of the two is equal to probability of providing times probability of 1 page? I can't say that because they are not independent, right? So whether you're not sure they are independent or not, use the other equation, which is always correct, right? So the other equation that was always correct was the following. That is, this is always equal to probability of providing information given 1 page times probability of 1 page. This is always correct. It's not, even if they are independent, this is correct, right? So that's why it's safe to use. And this is equal to, so I have probability of P given 1 page, that's 0.1, times probability of 1 page. Probability of 1 page is 40%, so 0.4. So this is the first part, right? So we just calculated the first part. And the rest is quite similar, right? The math is the same, right? So the math, all of the math is here, right? So this is the part that I calculated, right? Right? And we have 4 terms that we need to add up, right? And at the end, the probability is 15%. So the answer to this one, probability of providing information is 0.15. Right, so we answered part A. Any questions about part A? Okay. So now part B says if a visitor provides contact information, what's the probability that the visitor viewed 4 or more pages, right? So another thing about conditional probability is that the way we say them in English is usually the other way around, that we write them in math, right? So the math, so we usually say, if A happened, what's the probability of B, right? So when we say in English, we say, oh, if if a visitor provides contact information, that means that, oh, I know that A has already happened, right? We start with the condition in English, right? So if a visitor provides contact information, that means that this part is asking, calculate, so I'm just reading the first part of the question, right? Calculate probability of something given that the person provides contact information. So given P, right? So this here, this highlighted region here, this highlighted phrase corresponds to given P, right? If a person provides contact information, that means that P happened, right? Now let's see what the question wants. What's the probability that the visitor viewed 4 or more pages, right? So it wants 4 or more. 4 or more. Right? So from the previous, from the stuff we wrote here, we see that we have the other way around, right? For example, we have probability of providing information given that the visitor views 3 pages, right? Now this question wants the other way around, right? It's flipping the order, right? And because of that, we have to use the Base Theorem, right? So this is going to be equal to probability of providing contact given 4 or more given, oh sorry, I already wrote the given part. So this, so probability of providing given 4 or more times probability of 4 or more divided by probability of P. Right? So I'm not happy, what I wrote is quite small, so I write it down here. So this thing, I'm going to use the Base Theorem, is equal to probability of P given 4 or more times probability of 4 or more divided by probability of, so here we have P, so here is also going to be P. Right. And always when you use the Base Theorem, the denominator is the difficult part to calculate. Unfortunately, we calculated in the previous part, right? In A, we calculated probability of providing information, that's 15%. So this is going to be equal to 15, right? Probability of providing given 4 or more That's basically these 40%, right? So this is probability of providing information given 4 or more. So that's 0.4 times probability of 4 or more. That's this 10% up here. That's it. That's the answer. So this is equal to 0.267. 267, right? Or the number is also here, 267. Any questions? So the next part of the question says, compare your result with 10% probability that a visitor visits 4 or more pages, right? So if we look here, there's a 10% chance that a visitor visits 4 or more pages, right? In general. And now we see that if we know that, that person provided information, probability of 4 or more is basically 26%, right? So if I just create a new page to summarize these. So in general, probability of 4 or more is 10%, but probability of 4 or more, given that the person provided information, that's 267, right? So we see that they are not equal, right? So these two are not equal to each other, and that means that they are not independent, right? So we should be glad that we didn't, here, here, we didn't assume they are independent, because that would have been wrong. We just use the equation that's always correct. And intuitively, this makes sense, because in general, only 10% of the visitors 10% of the visitors visit 4 or more pages. But if you know that that person provided contact info, then there's a higher chance that, that person visits 4 or more pages. It's 26%, right? So after you solve a question, it's a very good idea to analyze your answers to see if they make sense. Any questions? Okay, so that's it for this chapter. Now let's move on to chapter 3. So at the beginning, chapter 3 is quite abstract, maybe the first 5 to 10 minutes, but bear with me, it's going to make sense, right? So at the beginning, we are going to introduce the concept of a random variable, right? But before we do that, let's solve a question, right? Because we can relate more to this question. So assume that we have, some camera flashes that we are testing. The time to recharge the flash is tested in 3 cell phone cameras, right? The probability that a camera passes the test is 80%, right? So there's an 80% chance that we pass the test. Right? And we assume that the cameras are independent from each other. Right? So the probability that the first and second cameras pass and the third one fails, we are going to denote that as PPF, right? Pass, pass, fail. And since the question says they are independent, I can multiply them, right? So this is very important. The reason this equality is correct is that the question says that, so this equality is, in general incorrect. But the reason I can just multiply probabilities is that the question says they are independent. right? So probability of PPF is going to be 12%. So we have other outcomes in addition to PPF, right? Like we have PFF, we have FFP, we have so many outcomes that can happen, right? So let's try to tabulate them, right? So these are all of the outcomes that can happen. For example, all three of them can pass, right? So probability of all three of them passing will be probability of PPP is going to be 0.8 to the power 3, right? And that is this number, 512, right? So this table basically shows all of the possible outcomes, right? So if we count, there must be eight rows here, right? So 1, 2, 3, 4, 5, 6, 7, 8. Yeah, so this table is complete, right? It considers all 8 outcomes, all possible 8 outcomes. Right? And all of the probabilities are here, right? So all of them, since they are independent, these numbers are quite easy to calculate, right? Any questions about basically how we get these numbers in this table? This must be very easy for you now. We just multiply probabilities, right? Now, yeah.
So if it didn't say it was independent, we wouldn't be able to multiply it.
Yeah, that's a very good question. So if the question didn't say they are independent, right, it just tells us that probability of one camera passing a test is 80%, right? And we don't know whether, if one camera fails, does the other camera, the chance of other camera failing increase or decrease, right? If the question doesn't say that, then we can't proceed. We can't solve this question, right? So here what we are going to do, so listen very carefully because this concept is very, very tricky, right? I'm going to introduce the concept of a random variable x, right? So I say x is the number of cameras that pass, right? So capital X is the number of cameras that pass, right? And capital X can be 0, right? Because none of the cameras can pass. It can be 1, it can be 2, and it can be 3, right? Because I'm testing 3 cameras. So this last basically column in this table denotes X, right? So if the event is pass, right? If the event is pass, then X is 3, right? Or if the event is fail, then X is 0, right? Now, what is interesting is that now I can basically, instead of writing, remember so far, we wrote everything as, probability of, set A, right? A was a set, right? Like A was a collection of outcomes, right? For example, A can be the event PF, right? In that case, probability of A will be this number, right? But what I can do now with this, introduction of a random variable is that I can say, what's the probability of X equal to 0, right? So X, random variable being 0, is basically this guy here, right? So 0.008, right? Or I can calculate probability of X being equal to 1, right? Yeah, or 2 or 3, right? So if you know the answer to this one, raise your hand. How do I calculate this? What is this from the table? Don't say it out loud. I want to also use this as an opportunity to learn one more name. So what is probability of X equal to 1? No, Vishai, thank you. Yeah, go ahead.
I'm not sure, but I think it's 0.032.
Yeah, so that's a good start. So from here, you're saying that is 0.032.
Yeah.
But look at the table, there's other ones.
Do we add them up?
Exactly, yes. We have to add them up because all of these, so let's use another color. So this, and this, all of them show, the outcome that x is 1, right? So for x being 1, either one of these 3 rows, can be the case. So we have to add them up. What is your name?
Gina?
Say it again.
Gina?
Gina? Yeah, like Gina Cody?
No, it's Rana, but it's...
I see, okay, all right. So this is going to be 0.32, as Gina said, right? Plus, so basically we can multiply by 3. Let's not add them, right? Because it's 3 of them, right? If you look at this table, there's 3 of them and they are equal, right? We just multiply by 3. So whenever, later on, in fact, in the rest of this course, we are always going to write probabilities as, like here we are going to write a variable. Whenever you get confused, what is this variable, you can come back to this example, right? So x is, we somehow relate the outcome to a number. So a variable, a random variable is a variable that associates a number with the outcome of a random experiment, right? And it's a function that assigns a number, a real number, to each outcome in the sample space. And we denote a random variable by capital letters, capital X, right? So for example, the measured value of the random variable after doing an experiment, the measured value will be shown as small x, and the actual random variable will be shown as capital X, right? So, for example, in the previous example, we wrote the random variable with capital X, right? So this is our random variable. And a certain outcome, for example, 1, we denote that as x, right? So when we write small x, that means that it's one outcome of a random variable, right? So x is a certain outcome of the capital X, right? So for example, if we are measuring, current and it's in milliamps, then we want to calculate probability of, our current being, 70 milliamps. And random variables can be discrete or continuous, right? So for example, let's say I'm measuring, some currents in a circuit, and the current is between, I know that the current is more than 0, and let's say it's less than, 5 milliamps, right? So here x will be a continuous random variable, right? Or let's say you define your experiment as the time that it takes in seconds until the next customer visits Tim Hortons, right? So then x will be continuous random variable because time is continuous, right? Okay, so let's look at some examples. So let's say we have a surface and we are looking at the number of scratches on the surface. That's a discrete random variable because number is a discrete, right? It can be 1.5 scratches. Or let's say number of potholes on a street, right? That's a discrete random variable. or proportion of defective parts among 100 tested, number of bits transmitted in error, number of common stock shares traded per day, right? These are all discrete random variables. And in an experiment, the current can be continuous random variable, length, weight, time, temperature, pressure, right? Okay. So if we go back to this example of the camera flash, right? From this table, right, from these numbers here, I can calculate P of x equal to 0, P of x equal to 1, equal to 2, and equal to 3. Right? Now, you might ask, why do I do this? You know, like, why don't I write a probability of, you know, PPF, like write them as sets? The reason is that now P is a function, right? Because what is a function? You give it it has an argument, you give it a number, it gives me a number back, right? Now P becomes a function, right? That's the cool part about it. I can actually plot P, right? I can say P, and I can say X, right? So X can be 0, 1, 2, and 3, right? And this function is going to be like this. So P of 0 is 0.008. P of 1 is 0.096. P of 2 is 0.384. It's a bigger number. And P of 3 is, yeah, I didn't plan ahead. So this guy is 0.5, right? And this number, right, is 0.5, right? 0.512. So now I can plot P as a function. And that's why we are doing all of this. So this plot that you see is called PMF, probability mass function. The formal definition is in a few slides. We'll see that. Any questions? Okay. So the probability distribution of a random variable x gives the probability for each value of x, right? So if I have the probability distribution function, then, you know, if you tell me that, let's say x is continuous, right? And this is p, right? If you tell me that, you know, the function is like this, right? If you know this function, then any outcome is easy to calculate. You know, you say, oh, I want x to be between, you know, let's say 1 milliamp and 2 milliamp, right? All I do is I say, oh, that's basically it means that you want this to be here, right? So we will be doing a lot of these in this course. Okay, so we define probability mass function is basically is defined for a discrete random variable x, right? And this random variable x can take x1, x2, all the way to xn values, right? So basically, f of x, so probably the third one should be first, because that's the most important one. So that's the definition of PMF, right? Probability of x equal to xi is going to be denoted as f of xi, right? So here, for example, this is f of xi, right? So f of xi simply means that x, that random variable, is basically some outcome xi. Right? Now, can somebody say in plain English why these two are correct? Raise your hand if you know the answer. So the third one was the definition of PMF. So f is called PMF, right? This is the definition. Right? Why are the first and second, like what is the intuitive meaning of the first and second? Not Vishai? Not Gina either. Yeah, first say your name. Say it again. Arias? Yeah, okay. All right, go ahead, Arias.
First says that the probability of an outcome cannot be negative.
Exactly.
I feel like that's pretty intuitive. But, and the second one says that the sum of probabilities of all outcomes is equal to 1.
Yeah, exactly. So those two are axioms of probabilities, right? Remember we said, probabilities can't be negative, right? So that means that f of x is always positive, right? That's the first, right? You can't say, an outcome probability of something happening is like minus 10%, right? That's impossible. Probabilities are always between 0 and 1. And the second one says that the sums are actually 1, right? And that means that the total, the total probability is 1 if we look at all the outcomes, right? And in fact, there's one more thing here that, if x is discrete, so if x is discrete, which is what we are considering here, then there's one more thing, f of x must be less than or equal to 1, right? I don't know why this slide is missing it. Probabilities are always less than 1 or equal to 1 maximum, right? So perhaps we can amend the first one by this, right? F of x is always between 0 and 1. So let's look at one example. So I'm rolling a die, right? And this is my P of PMF, right? So for x can be 1 to 6. So here in this case, it's very intuitive, right? So x, we can denote x as the number that shows up when I roll a die, right? So probability of any x is 1 divided by 6. It's a uniform distribution. It's constant. Any questions? Okay. So let's look at another example. So x here is my random variable, and x is the number of wafers that must be analyzed to detect the first contamination, right? So basically, I have the question is as following. These are basically the bullet points of the important information about the question. I have, a big bag, let's say it has infinite number of wafers inside, right? So let's say you're at a company, that company has practically like infinite number of wafers. Let's say you want to find the first wafer that is defective to analyze it, to find out why it's defective, for example, right? So basically, x is the number of wafers that must be analyzed to find the first contamination. Once you find the first contamination, you abort the experiment. You're done, basically. That's success, right? Because now you will analyze that to find out what's going on, for example, right? And assume that the probability that a wafer contains contamination is 1%, right? So a particular wafer containing contamination is 1%. Wafers are independent from each other. That means that if I check, 100 wafers, and all of them are, not contaminated, I can't say, probability of having a contamination was 1%. I already tested 100. They were all not contaminated. So for sure, the next one is going to be contaminated. That's wrong, right? Because the question says they are independent. Even if you checked, 1,000 wafers, they were all clean. The probability of the 1,001st one is going to be still being contaminated is still 1%. That's what independence means. The question wants the probability distribution function for x, right? So we denote being like having contamination as with p, like contamination being present, and we denote a as contamination being absent. So this line is very important, right? What is the sample space? Sample space is the following. It's either P, it means that the first wafer that you check, you're very lucky. The first one has contamination, right? So if the first one has contamination, you abort the experiment. That's success, you're done. You don't need to check anymore, right? Or AP, right? So this one means that you check the first one, it's absent of any contamination, but the second one does have contamination, right? So you abort the experiment, you're done, that's success, right? So the third basically element in this set means that you check two, both of them are absent of any contamination. You check the third one, a contamination is present, so you abort the experiment, and so forth, right? So if I want to write more of these sets, so the next one is going to be A, P, and then the next one is going to be A, P, and so forth, right? So the range for X can be 1, right? So let's say I'm very lucky. The first one that I pick, has contamination. Or the second one, or third one, or fourth one, X can go all the way to infinity, right? So there's no end for X. I can, keep, flipping a coin, and I always get ahead. Let's say the experiment is I want to get the first tail, right? So once I get the tail, I stop the experiment, right? So X can go all the way to infinity, right? So probability of X being 1 is, so that one part being having contamination is 1%. Probability of X being 2, so that means that I want this outcome to happen, right? I want AP to happen. So that means that the first one should be absent of any contamination, that's 99%, and the second one be present, right? So why do I multiply? Because they are independent, right? Otherwise, I couldn't have multiplied, right? So that's this number. And then X equal to 3, it means that I should have, so that's X equal to 3. So here I have a total of 3 total experiments, right? So in this case, I'm testing three parts, right? And the first two should be absent of any contamination, and the third one should have the contamination, right? So we multiply. Yes?
So when X increases, okay, the probability is decreasing. So
Yeah.
when, the summation of all of them will give us 1.
Yep.
1.
Up to infinity? That's a very good question. So the question is, so we can try to plot this, right? So that's an excellent question. So what we can do is we can plot this function, right? So for X equal to 1 is 1%. So that is 0.01. So this is P, and this is X, right? So X equal to 1 is 1%. X equal to 2 is a little bit lower. X equal to 3 is a little bit lower. And this is, by the way, the exponential function, right? So it decays. So maybe I should not. This is not a continuous function, right? So I just plotted this to show the trend. It's just these guys are the function, right? It's not continuous, right? And if you add up all of these, so P of X equal to Xi, summation of these from Xi equal to 1 all the way to infinity, that's 1. Yeah, this is called, I think it was called the geometric series, right? There was a proof for this. Okay, any questions? Okay. Okay, so now let's introduce another concept. So the concept that we saw already is PMF, right? Probability mass function. And by the way, in the next chapter, we introduce another concept so here our X is discrete. And if X is continuous, the other concept is called probability distribution function, right? And that's called PDF. they are very closely related. The only difference is that for PDF, X is continuous. For PMF, X is discrete, right? But PDF is much more commonly used. So even like when I say, when I want to say PMF, sometimes I say PDF because PDF is a very common word. Not because of the PDF file format, but in probability is a very common word. So basically here, summation of P of X for all X is 1, right? So the next concept that we are going to introduce is CMF, cumulative mass function, right? So CMF is, let's look at basically the same experiment, right? So I'm rolling a die. In this case, X means, if I get 1 or 2 or 3, right? So in this case, I basically say what's the probability of getting, my X being less than, let's say 4, right? Which is equal to P of X equal to 1 plus P of X equal to 2 plus P of X equal to 3, right? So in CDF, right, is cumulative, meaning that we add everything from, minus infinity to, whatever point we want. So in this case, because when we roll a die, we can't get minus infinity, the minimum number is 1, my summation starts from 1, right? So if we look at the table, this column shows X, right? And this column shows the probability of X being less than some number, right? So probability of less than or equal to. So probability of X being less than or equal to 1 is 1 divided by 6 because the only outcome is 1. Is being less than or equal to 2. This here means that, it can be either 1 or 2, right? So this is going to be P of X equal to 1 plus P of X equal to 2, right? And then this one is going to be, again, the same thing. P of X plus 1 plus P of X plus 2 plus P of X plus 3. Equal to 3, right? So the concept of CDF, cumulative distribution function, says that I want my X to be less than a certain number, right? I don't say, is equal to something. I always say less than something, right? And you might question, quite rightly, why do I care less than? Why don't I say more than, right? So we'll see later on, less than has very nice properties, right? In fact, you probably have noticed already that CDF is the integral of PDF, right? So summation, when we say less than something, when we add up, that's actually integral, right? We'll see that later on, right? So the reason why we define, this less than thing is that this is equal to, for the discrete case, sigma from minus infinity to that point. And for the continuous case, which is, a big focus of this course, this will be the integral from minus infinity to, x to that point of, f of x, d of x. Right? So that's why we introduced CDF. That's the reason. Okay, so let's look at our recurring example of, camera flashes. So we have 3 cameras, 1, 2, 3. Each one of them can pass or fail. So for example, all 3 of them passing is, this number here is 0.8 to the power 3, right? So 0.8 to the power 3 is 512, right? And we already calculated this, right? We already calculated P of X equal to 0, P of X equal to 1, 2, and 3. Right? So what we want to do now is we want to calculate CDF for this example, right? So this comes from previous slide. And the question wants, find the probability of 2 or fewer cameras passing, right? So that means that if I denote x as the number of cameras that pass, I want x to be less than or equal to 2, right? So that means that either x is 1 or 2 or 3, right? And remember, whenever we say or, we have to add, right? So that is going to be p of x equal to 0 plus p of x equal to 1 plus p of x equal to 2. Okay, so now that we saw an example, we can formally look at CDF and its properties. So symbolically, for a discrete random variable x, we denote CDF as capital F, right? So it's quite like your calculus, you know, that we denote, you know, small. The integral is usually denoted with capital. That's quite similar. So f of x is equal to p of x less than or equal to x. And actually, I don't know what's here. I think this is equal to sigma. Yeah, so this is equal to sigma f of xi less than or equal to x. So f of x is p of x less than or equal to small x, right? And summation of f of x for all x less than x, for all xi less than x. Now, f of x is always between 0 and 1, right? That means that, you know, when we add probabilities, first of all, because those probabilities are positive, we can never be negative, right? So that's why it's more than 0. And also, you know, we know that the probability of everything happening is 1, right? So fx at the end should be 1. It can't be more than 1. The third one is a bit more complex. Can anybody say why the third one is correct? So this has a name in your calculus, right? So if a function, if y is more than x, f of y should be more than f of x, right? And these functions are called, does anybody remember what's the name of these functions? That if x increases, y also increases? Raise your hand if you know the name of. So these functions, this is not related to this code, but it's called monotonically increasing. It means that if x increases, f of x also increases, right? There's no chance that f of x decreases. But it's a bit, you know, it's not difficult, but it's a little bit, it requires, you know, a little bit of like good understanding of why this is correct. So do you know why this is correct? Does anybody know why if x increases, f of x also increases? No, not Vishai? Anna, right? Yeah, go ahead.
Well, whenever I think about integrals, I only think about velocity and acceleration.
Okay.
So for example, if your velocity is increasing, then your acceleration has to be increasing. That's how I think about it. Like,
Yeah. So Anna's answer is like a physical analogy. So you're saying that if acceleration is, for example, positive, that means that at every time your velocity, which is the integral of acceleration, should also increase. Yeah, that's correct. Yeah, that's a very good answer. Right. So basically, to answer that, right, we know that we know that f of x is a summation of probabilities up to x, right? So let me try to give, you know, another explanation. So your explanation was perfect. Let me see if I can explain another way. So this is f, right? And for every x, you know, I know that f of x is more than 0, right? Now, if I tell you that, you know, so this new plot is capital F, right? If I tell you that f of this x is the summation of PDF up to this point. And f of, which one is, yeah, y is bigger, right? So an f of this y is summation up to this point, right? And by the way, those things that you're summing are positive, right? That means that this should go up. This has no other way, right? Or stay constant. When does it stay constant? Yeah, exactly. When this guy is 0, right? When probability is 0, this guy stays constant. And when probability is non-zero, this guy goes up. Right? So I will explain